Dream to become the next Sir Isaac Newton or Albert Einstein? Learn calculus from Refath Bari, aka 800/800 guy, is teaching calculus this year. Watch his videos.
Hello folks, so back with another episode of calculus. Let's take a look at proving the limit as x approaches 0 of sine x over x. So how do we prove what this limit is? Well, usually we try to take an analytic approach to these kind of limits, but today we're going to be trying to look at this geometrically. Now, how do we look at sine of x geometrically? Well, remember, where does sine of x come from? It comes from the unit circle, and that's where we're going to go back to, the good old unit circle. So we have the unit circle here, and today we're going to be trying to prove that the limit of sine of x over x as x approaches 0 is equal to 1. How are we going to prove it? We're going to use something called the squeeze theorem. Now, if you don't know what the squeeze theorem is yet, I'll give you a brief introduction. The squeeze theorem says that if you have three functions, f of x, g of x, and h of x, and f of x and h of x both approach the same limit as x approaches some constant c, then g of x will approach that same limit. So how do we express that in notation? If the limit of f of x as x approaches c equals L, and the limit as x approaches c of h of x equals L, and f of x is greater than g of x is greater than h of x, then the limit, the limit as x approaches this constant c of the middle function, this g of x, must also approach L. Now, right now this is just notation, it doesn't mean anything, but you'll get a clearer understanding of what I mean by taking a look at these diagrams. So let's go ahead and get started with the unit circle. So why am I drawing the unit circle here? Well, I'm trying to involve sine theta somehow in this diagram. So first thing I'm going to try to do is find the area of three triangles. You'll see why at the end. So let's draw in these three triangles. Alright, good enough? Okay, so let's start with the first triangle. We want to find the area of this triangle. So seems simple enough, right? You have theta and you want to find the area of the shaded figure. So how do we do that? Well, this is a unit circle, right? So the hypotenuse is going to be 1. So that means sine of theta is going to be whatever this height is. Let's call this height h, I don't know. So opposite over hypotenuse. So the height is simply going to be sine theta. So the height of this triangle is sine of theta. So we already have the area of the first triangle. The area of a triangle is half base. Remember, this is a unit circle, so our base over here is going to be 1 times height. We just found that the height is sine theta. So that means the area of this triangle, this shaded figure over here, is going to be sine theta over 2. Okay, nice. So next thing we're going to do, we're going to take it a step up. We're going to find the area of this sector, right? Okay, so hopefully you folks remember your sector formulas. It's theta over 360 times 2 pi r. But in this case, I'm going to be trying to work in radians just to simplify our measurements. So instead of 360, let's write 2 pi. Here we know that the radius of the unit circle is 1, so 2 pi will simplify to just just 2 pi. And oh sorry, this should be pi r squared. R is simply 1 and 1 squared is 1. So that leaves us with pi. And if you cancel these out, you'll simply get theta over 2. So yeah, that's the area of this sector, theta over 2. And let's come over to this last triangle over here. You'll see that we have 2 right triangles here, and they're actually similar to each other. Why, you might ask? Well, because these lines are parallel to each other, so these angles are going to be corresponding, these 2 angles. Okay, so how do we find the area of this triangle? Well, let's try to use the information we gathered here. First things first, we know that this height is sine theta, right? Recall from the first area problem that the height of the small triangle is going to be sine theta. Now, by the same reasoning, the base of the small triangle is going to be cosine theta. If you don't understand why, let me show you right now. It's because we know that the hypotenuse of the right triangle is 1. We know that the height is sine squared theta, and we're trying to find out the other leg. Let's call that L2 squared. Well, if you recognize this, this is just the Pythagorean theorem. It's a very common trig identity. Recall that sine squared theta plus cosine squared theta is 1. That means the other leg must be cosine theta. So that's why this leg over here is cosine theta. Now recall that a unit circle has a radius of 1. So this whole leg will be 1. If this is cosine theta, then what's left over will be 1 minus cosine theta. Right, okay. So why did I put that? I put this measurement over here so that I can make similar triangles. At the end of the day, what I want is to find out the area of this triangle. I already know the base, I just need the height. So how do I find out the height? Well, I use similar triangles. Let's call this height, I'll call it h, right? So let's do some similar triangles. Sine is to cosine as h is to 1. Let's do that again. This leg over here of this small right triangle, sine, is proportional to this leg over here of the smaller right triangle, cosine. So sine theta over cosine theta is proportional to h over this big leg, which is simply 1. So if you recognize this, this becomes tangent theta is equal to the height of this big triangle. So let's just simplify that. Let's call that tangent theta. But we're not done yet. Remember, our goal was to find the area of this right triangle. Area of a triangle is simply half. Base is 1, and height is tangent theta, as I just showed. So that means the area of this triangle, this right triangle, is going to be tangent theta over 2. But how does that help us find sine x over x? Well, the thing here is that we found 3 different areas, and we know the relationship of these 3 areas to each other, right? Let me show you what I mean. We know that this is the smallest area, this is the medium area, and this is the greatest area. And you can see that intuitively by just looking at the picture. So let's write that down as an inequality, right? So we have sine theta over 2, right? That's the smallest area we have, is less than theta over 2. That's the second largest area we have. And our largest area is simply tangent theta over 2. So at the end of the day, we want to get sine x over x restricted by 2 other functions, right? We want it to be surrounded by 2 other functions that approach the same limit, so that we can use the squeeze theorem. But here we see that sine theta is not restricted by anything. In fact, it's to one of the, it's like the corner of the inequality. So what can we do? Well, first things first, you can simplify this inequality, right? Multiply the whole inequality by 2, so that we get rid of these fractions, right? That's pretty easy enough. Let me just move these up. The next step, however, might not be as intuitive. The next step we're going to do is take the reciprocal of all three of these terms. So when we take the reciprocal of sine theta, theta, and tangent theta, the inequality sign is going to flip. It's almost like you're multiplying by a negative sign. So 1 over sine theta is greater than, we're taking the reciprocal, so 1 over theta is greater than 1 over tangent theta. And now we're gonna, if you see what I just did here, we're just one step away from checkmate. We just have to get sine x over x. We already have theta in the denominator. So that means if we multiply this inequality by sine theta, we've hit jackpot. Why? Well, if you distribute sine theta to this inequality, you'll get 1 on the left-hand side. You'll get sine theta over theta, which is what we've been looking for all this time on the numerator. Sine theta over theta. And over here you'll get sine theta over tangent theta. Sine theta over tangent theta. Okay, so this is great because now we have what we want exactly in the middle, sine theta over theta. It's restricted by two functions, y equals 1 and y equals sine theta over tangent theta. Now we just have to find the limit of these functions as x approaches 0. But before I do that, let me just simplify this right-hand side over here. If you notice, tangent theta is simply sine over cosine, right? If we simplify this, what will we get? Well, multiply top and bottom by cosine. Sine theta times cosine theta over sine theta. Sine and sine cancel out. So that means sine theta over tangent theta is just cosine theta. So we've made our inequality even simpler. So this is our final inequality. 1 is greater than sine theta over theta is greater than cosine theta. And now we are almost at the final step. Let me erase this. We are almost at the final step, but in order to use the squeeze theorem, we have to find the limit of these two restricting functions as x approaches 0. So let's do that. So the limit of, first of all, we know that, let me call this f of x, g of x, and h of x, right? So I know that I already have the condition that f of x is greater than g of x is greater than h of x. That condition is satisfied. Now what I'm going to do is say that the limit as x approaches 0 of f of x equals the limit as x approaches 0 of g of x equals the limit as x approaches 0 of h of x. And how do I know that? It's because of this inequality, this restrictive inequality. So let me use that to my advantage. F of x, what is f of x? If you look over there, you see that f of x is simply 1. Let's replace this by 1. The limit of any constant as x approaches 0, that's simply going to be that constant, right? What about this? G of x. G of x is sine theta over, sorry, what am I saying? G of x is sine, G of x is sine theta over theta. And that's also equal to the limit as x approaches 0 of h of x. What is h of x? H of x is cosine theta. Okay, what is cosine theta as x approaches 0? Well, remember the unit circle, folks. As cosine theta approaches 0, remember, this point is 1 comma 0, right? So that means cosine is going to be 1 when theta is 0, right? So this whole thing approaches 1, just like the left-hand side. Okay? And now we have completed our use of the squeeze theorem to determine that the limit as x approaches 0 of sine theta over theta must equal 1. All right, folks. So thank you for watching, and we will see you next time.
Bari Science Lab to fall in love with math and science, especially programming.